So for our chemistry, we're going to look at atomic number and atomic mass number, right? Atomic number plus atomic mass number. And atomic mass number is, so atomic number, rather, is the number of protons. Ne? Number of protons. So in other words, if we're looking at just hydrogen, we know that hydrogen is one proton, one neutron, and one electron. So if an atom is existing alone in space, it just has the same number of protons as electrons. So if we're looking at hydrogen, then because it has one proton, we know that its atomic number is 1, and that's why on the periodic table it's placed at 1. And the mass of an atom depends on how many nucleons. Nucleon is this in the center. How many nucleons are in the atom, in the nucleus. And then when we add the number of protons to the number of neutrons, neutrons being those that don't have a charge. So proton would be this one, and neutron would be this. And these two are called nucleon. Right? All the things that have to do with an atom, they end with the suffix on. Do you know what a suffix is? Would you speak? Okay. Now when I did Sotho, we had this thing called Sifongapele and Sifongantao when you're building words. There's a thing that you put in front of a word, that's a prefix. Like uni, trans, para. Those are prefixes, right? So protons, neutrons, electrons have a suffix on. So because these ones are in the nucleus, they're called nucleons. They take on that suffix on, right? So protons and neutrons combined, they're called nucleons. Those are the subatomic particles in the nucleus of an atom. So when you add those, you get the atomic mass number, right? So on a periodic table, you'll have an element, call it X. Then the number there, A, would be number of nucleons. And the number Z would be number of protons. And this would be the symbol for the element. Okay, so yeah, number of nucleons. Again, the mass of an atom depends on how many nucleons the nucleus has. So the number of neutrons, so in other words, that's the atomic, that's the atomic mass. And what you will notice on the periodic table, I think the atomic mass is almost double the number of protons in this illustration here. So this one would be 2x this one. Give or take, roughly. Not exactly, but just roughly, right? So if we look at an iron, so if we look at the atom iron, it has 26 protons and 30 neutrons. And what this means is on the periodic table, it would look something like this. So that would be 56 and 26. Why? Because 26 is the number of protons, and the number of neutrons plus protons give us that atomic mass unit. So that's what we should know, the periodic table. All right, so if we quickly look at, use this example. we must use standard notation to represent the atom or the element sodium. Sodium. Do you know where we find sodium, Magdalene? Do you know where we find sodium? Yes. But it doesn't occur as sodium alone. It occurs as part of a chemical called salt, right? So, if we have the symbol for sodium as Na, by the way, Na comes from the Latin word natrium, which was the word Latins used to describe the metal sodium. And I think also in Afrikaans, that's what it's called, natrium. 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 So a lot of these chemical elements, their names are from Latin and Greek. So yeah, so sodium is number 11 on the periodic table. So it would have 11 protons. Yeah? So if it has 11 protons, then we'll put that down here. And then we also know that on the periodic table, it's got, so if sodium is neutral, it has the same number of electrons as proton, then its electrons are 11. Then on the periodic table, its atomic mass number is 23. So what does that mean? If we want to work out the number of neutrons, we will say 23 minus 11, which is 12, equals the number of neutrons. Why? So what does this basically tell us? It tells us that neutrons, number of neutrons, equals the atomic mass number minus the number of protons. So this examples, we don't have to do them per se because they're just a discussion on what we just touched upon. Now, remember, Nobita, I mentioned something about there being a radioactive hydrogen.
Yeah.
Yeah, so those are things that we call isotopes, right? So under normal situations, the chemical properties of an element depend on the number of protons and electrons inside that atom. So if we add or increase or remove or reduce the number of neutrons in an atom from the nucleus, then the properties will not change. But if we add protons, sorry. If we have, let me gather my thoughts. Okay, so if we have an atom and we increase the number of protons, then we're changing the atom. It's no longer, if it was one proton, then we know it's hydrogen. But if it has two protons, then it becomes helium. It's no longer hydrogen. But if we have the same hydrogen and we increase the number of neutrons, so let's say instead of one neutron, we add another neutron. So we have hydrogen there, one neutron, one proton, one neutron, and one electron, right? Then we add a proton. We will have something that has a different set of properties altogether. So two protons and one neutron. But no matter how many neutrons we add or subtract from a nucleus with 6 protons, that element will still be carbon. But if we have the same number of protons and a different number of neutrons, then we have isotopes. So in other words, not that we can have a proton added to another atom because that would take a great deal of energy to do. But if we do change the number of neutrons in the atom and we change its atomic mass number, then we have what we call an isotope. So in other words, if we increase the number of neutrons here, then we have an atom that is still hydrogen, but it has more mass. Because if we add that mass of a neutron onto another neutron, then the mass of the atom itself increases. And because it increases, we call these isotopes. Isotopes. So in other words, isotopes have the same number of protons but a different number of neutrons. And a bit of a discussion. So if chlorine 35 has an atomic mass of 35 units with 17 protons and 18 neutrons, an isotope of it will be chlorine 37, which has an atomic mass of 37 units, which is 17 protons but 20 neutrons. So the number of neutrons there increased, and because it increased, then it's an isotope. And I think the 37 illustrates the atomic mass of that isotope. Right, so I like this example. Chlorine has two isotopes, chlorine 35 and 37. The abundance of these isotopes when they occur naturally is 75% for chlorine 35 and 25% for chlorine 37. So I think that's interesting because it shows how you can find the isotopes of even normal elements. Like any atom in the periodic table can have an isotope and therefore be kind of radioactive. But it's not always the case that this happens. Most of the times, atoms show up in their normal state. I think the important discussion here, because Nobuhle, why we went back to this part is because we needed to talk about electronegativity. And that has to do with the electron configuration of atoms. So we're going to look at electron configuration because, I almost wrote election there. Sorry. Electron configuration, right? So electron configuration just means how the electrons are arranged in the atom. And if we look at something like helium, for example, let's say that's its nucleus, then it would have, I think, 3 electrons, yes, because it's number 3. So electron 1, electron 2 in the first orbital, and the third electron in the second orbital, right? So these orbitals, they're called energy levels. So I'll just put there. And Nobuhle, you're gonna have to pardon science here because it gets really messy. It gets really messy. I think the scientists did their best to describe these using all the tech that they could. But we're gonna try and get it as simple as possible, right? So these energy levels, they start at like close to the nucleus, right? Around the nucleus. And they're numbered 1, 2, and 3. So the energy level closest to the nucleus is called energy level 1. And then the one outside of it is called energy level 2. And each energy level has a specific number of electrons that it can carry at any given time. The closest to the nucleus will have the lowest energy, but the further away from the nucleus, you'll have higher energy. And what that means, in that thing that I was saying, it's a lot easy for the sun to have a stronger gravitational pull on Mercury than it is for the sun to have a stronger gravitational pull on Pluto. So likewise, we can think of the energy levels as follows. The energy level is lowest near the nucleus, but the further away the energy level is from the nucleus, the higher the energy. So we can imagine these energy levels as concentric circles around a nucleus. So these images, this one is lithium. It's from the same group of metals as hydrogen. Fluorine or fluorine will have an atomic number of 9, meaning it has 9 electrons. So when we use the same configuration, we'll have nucleus, energy level 1, and energy level 2. So around energy level 1 always takes 2 electrons. Ne? Energy level 2 takes 8, I think. And I think it changes vice versa as we go forward. But what I want to show here is we have 2 electrons. This is fluorine. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 2, 4, 6, 7. Oh, so we don't have an 8th one, yeah. 7, yes. All right, so the other thing with chemical reactions that we need to always keep in mind is that whenever a reaction happens, there's usually electrons being transferred from one atom to the other. So other atoms, like your group 1, would be donating electrons. For example, if lithium was to react with fluorine, what would literally happen is this electron would be donated to that gap there. And then this one would be lithium plus, and this one would be fluorine negative, because apart from its natural state where it's neutral, it's now received a negative charge, which gives it a net ionic charge of -1. So we're going to have these recur over and over and over. Now, in the same learning guide, they put neon there deliberately. And that's because neon does not really react. It's one of the noble gases. So because it doesn't react, it means it doesn't need to receive or donate electrons. It can just exist as it is. And that orbital is literally an orbital region where an electron will be found around a single object. So orbital is a region where electrons would move around freely in an atom. Okay, now we're going to discuss these orbitals, right? And the discussion is going to get a bit messy, but bear with us. So the first energy level has only got one s orbital. Ne? It's got one s orbital. And then the second energy level has got one s orbital and it's also got it's got 3 p orbitals. So 1 times s orbital and 3 times p orbital, right? Orbital just means where the electrons are going to move. And then the third energy level has got 1 s orbital. It's got 3 p orbitals and it's got 5 d orbitals. So from the nucleus, whenever you increase in energy, if that's level 1, that's level 2, that's level 3. So here you'll have the s orbital, you'll have the s and the p1, p2, p3, and then you'll have an s, you'll have p1, p2, p3, and then d1, d2, d3, d4, and d5. So that's more or less how the electrons are configured. And somewhere here you'd have your nucleus. All right, so each orbital can only hold 2 electrons, and electrons that occur in an orbital are called a pair, an electron pair. So 2 electrons per orbital. And these are called an electron pair. And then an electron will always try to enter an orbital with the lowest possible energy. In other words, what this means is electrons always try to find their way closest to the nucleus as possible. Ne? Voila. Okay. And then again, an electron will try and occupy an orbital on its own rather than share an orbital with another electron. But the same electron would also rather occupy a lower energy orbital with another electron before occupying a higher energy orbital. So, in other words, within one energy level, electrons will fill an s orbital first before going to a p orbital. What this also helps us to think about is when we have to do exercises where we do electron configuration on atoms, we first start with the energy level 1, then we go to the second energy level 2s, and then the other 2p's, then 3s, 3p, and so on and so on and so on. So we fill them up in that order. We start from 1s, then we go to 2s, then to 2p, then to 3p, and 3s and 3p. All right, so I'll just put here. So electrons fill up orbitals from lowest energy level to highest. And also, they would rather share with an electron before moving to a higher energy level. So they'd rather share an orbital before going to another energy level, before jumping up. All right. So we're going to use what they call, I think, what are they? Aufbau. I don't know what Aufbau means or who that is, really. But I just want to get some background. Who's Aufbau? Oh, okay. I thought so, because Bau means built in German. So Aufbau is a term which was used in publications from 1919 to 1947 in the German language. And they mean structure or construction or rebuilding and whatever. Okay, so the Aufbau principle is literally the principle with which we build electrons. Alright, so we're going to use Aufbau. So it's literally a principle we construct atomic structures, because we can't construct the atom, but we can construct its structure. All right, so we need to first find the number of electrons that the atom has. 2, fill s orbital up. Then 3, fill the second energy orbital. Then fill 2s, 4. Then we put 1 electron in each of the 3 p orbitals, 1 in each p orb. And then if there are still electrons remaining, we start again at the p and then we fill up. So if there is surplus, we repeat the step. Repeat step. All right. And then 5, we repeat, basically. So we're going to do not that people fill up a bus or a train like that. I mean, people sit randomly in buses or trains. But the principle is start with the empty seats first and then fill up as you go. Hans' rule and Pauli's rule. Hans' rule is that electrons would rather be in a subshell on their own than share a subshell. This is why when you are filling the subshells in, you put 1 electron in each subshell and then go back to fill the subshell. Whereas Pauli's exclusion states that electrons will have a property known as spin, and 2 electrons in a subshell will not spin in the same way. So that's why we draw electrons as 1 arrow pointing up and 1 arrow pointing down. Oh, okay. I see. Okay, so what this means is these are Aufbau diagrams on page 83 of the learning guide. And we start off by filling this orbital first with 2 electrons, then we move to the next one. Then when we get to the next one, we fill again. And if we still have electrons, we start filling up the p orbital. So to be 3p, the first one, we put 1 electron to show going up, and the second one to show going up, and the third one. And then if there's still some remaining, we fill up the same p orbitals, but with electron arrows going down, down, and then that would be the electron that's outstanding on the side, right? So this would be for fluorine. And then argon, which is a noble gas, will have something that looks like that. So the same fluorine that we had on the other diagram, which looked something like 1, 2, 3, 4, 5, 6, 7. Its Aufbau diagram would look something like this. So this would be the 1s orbital, 1 electron, and the second electron. That's how we fill them up, right? So that would be this electron. Let me use color. So this electron and that one would be these 2. Then we fill up the second orbital, the second energy level, which would be this one, 2s, and we fill it up with a second electron, a second pair of electrons. So those would be, maybe let's say these 2 for now, for argument's sake. All right. And then we're gonna go into the p level orbital in this. So this energy level is on its own level, and this one is on its own level. So here we've got the 3p orbital. Remember I said the conversation is gonna get a bit nasty. So this is the nasty part. So we fill up first with electrons, 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 and then because we can only count 1, 2, 3, 4, 5, 6, 7, we need to fill up so that we have all the electrons are counted for. So I've put in 7 there, so that means 1, 2, 3, 4, 5. So these are the 5 that I've already included. And now because we still need to fill up the energy level, then we fill them up, and this accounts for the remaining 2 electrons. So that's that. All right, so the same fluorine, this would be, what do we call this model? We call this model a electron arrangement. And this would be an Aufbau diagram. All right, so that's the long and short of it. So here, Hans' rule is that electrons would rather be in a subshell on their own rather than share a subshell. So it's like this, right? And then when we fill up, we start off by, like if we're doing energy level 1, we start off by this because we know electrons would rather be on their own. But since there's a pair, then it has to be paired up. Then we jump to the next energy level. Now in that energy level, we'll start with the lowest, we'll do the electron pair, and then we move to the 3p energy level. And what happens is we fill up first with electrons in each subshell, and once we fill them up, we then add their pairs. So after adding the electrons, we then add the electron pairs. So that's why this one here has got one arrow. We don't say 1, 2, 3, 4, 5, 6, 7, 8, 9 and fill them up like that. No, we fill up first, and then we fill up with the remaining so that we can add like that. That's how we follow the process. Okay, and then the last important thing about this Aufbau diagram is that when we write the electron configuration, we will say it's 1s, there are 2 electrons, 2s, there are 2 electrons, and 3p, which has 2, 4, 5 electrons. So fluorine has an electron configuration of 1s2, 3s2, and 3p5. Okay, so when a neutral... Okay, so we also have Aufbau diagrams for ions, ION, not iron. When we have that atom lose an electron, it becomes positively charged, and we call it a cation, right? So there's 2 types of ions. There's cations and anions, right? Normally, elements in groups 1 to, I think, carbon's group, which is 4 or 5, when they donate electrons, they end up becoming positively charged. So these are called cations, right? So after an element has donated an electron, it becomes positively charged. And similarly, when an element has received a charge, then it becomes negatively charged. And the importance of this is that it helps us with even the reactions, right? It helps us even with the reactions. But the great thing about this is that it helps us visualize the whole electron exchange between atoms. So for example, in this question here, we're given O2, which has just received 2 electrons, right? So we must draw an Aufbau diagram. So draw an Aufbau. So we know that we've got the 1s orbital, and then we've got the 2s orbital, and the 3p's, and I guess we'll have similar there. So on our periodic table, we will... Oh wait, which page is this before I scroll maniacally? It was oxygen, yeah. So for an ion, this was page 84, 85. So I just wanted to refer to our periodic table, right? Ah, yes. Where is it? There it is. There it is. All right. So oxygen is in group 6. 7, 8, yeah. It's in group 6. So it's those elements that are likely to receive 2 electrons. So if it's going to receive 2 electrons, that means here it's on, it's 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has 8 electrons in its neutral state. So let's start there. So 1s, 2s, 3p, 3s. Okay. So we fill up first orbital, arrow 1, arrow 2, next energy level, arrow 1, then arrow 2. Then the next energy level, we said it's got how many? 8, ne? So we've got 4, 5, 6, 7, 8. Let me, in fact, let me put this one like this, 8, yeah. So now because our atom is now an anion, it's an ion, it means it's received 2 electrons, right? So if it's received 2 electrons, then we fill those up here. So when we fill those in here, then it means the oxygen has now moved from having 8 electrons to having 10 electrons, so that it's kind of like neon. But now in ionic form, the Aufbau diagram simply shows us that the electron configuration would be 1s2, 2s2, and 3p6, 84. So let's make that 88. Yeah, so far back. Nitrogen. This is still nitrogen, yeah? For an iron. Oh, snap. This is not 3p, it's 2p. Because it's energy level 2. Yeah. 2p6. Yes. So when we place the 6 electrons in the p orbital in the second energy level, then we got 2p6. And the final answer looks something like that. All right. And then Nobuhle is still there. Because it's going to get really crazy. It's going to get really, 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 really crazy. Right? Remember our orbitals are 1s, 2s, and 2p, and then 3s, and then 3p, and then we've got the d ones, right? So our orbitals, apparently they don't just look like a orbit like the planets move around the sun. No, instead they're shaped like, I guess, dumbbells. So let's say you have a nucleus of an atom there. Right. Then the first energy level would be around it. That's where you find the first orbital of electrons 2. And then the second orbital, I get s orbitals are spherical. So the second orbital would be like this. And then that would be 2s. And the p's would, because they're in the same energy level, they would look something like this. 2 and maybe 3 there. So effectively what happened, oh, it kind of looks like a flower. All right, so what will effectively happen is in the lowest energy orbital, you'll have your electron there and your electron there. And the second energy level, you'll have another electron there and an electron there. Then in the other energy levels, you'll have electron, since that goes with that, those 2, and that goes with that, and that goes with that, and that goes with that. So they're kind of moving around the nucleus like it's some kind of joyride. You see how trippy it gets? Yeah, so it's not very easy to imagine how the orbitals look. But what I try to illustrate is more or less how these would look, give or take. But effectively, in the p orbital, maybe let's say you have one electron there and another there. So this one would sort of move like this and the other would move in the other way, all the way around repetitively, over and over and over and over. And that's what's happening with every atom anyway, whether it's the atom that makes the hydrocarbons in your cell phone cover, or the atoms of the oxygen in the air, or the atoms in the hydrogen in the water, or oxygen in the water. It doesn't really matter. But as soon as you have more than one s orbital, then you'll have this kind of shape for every atom. At least that's where the electrons move. So you don't really see them like this under a microscope, no, but it's an illustration of how the electrons move around. So in the s orbitals, because it's spherical, they'll move all the way around like you're globetrotting. But in the p orbitals, which are dumbbell shaped, there's only a limited movement. But that's because if two electron pairs fill up one p orbital, then other pairs will fill up the other two p orbitals. And I think, Nobutle, last time we spoke a little bit about valence electrons, right? And these are the electrons now that get heavily invested in chemical reactions, right? First, let's look at the word valence. Do you know what it means, Magdalene? So, right, the combining capacity of an atom or group of atoms as determined by the number of electrons it can lose, add, or share when it reacts with other atoms or groups. Right, so, and this also now extends to the integer or the number that is used to represent this capacity to either share, receive, etc., or donate electrons, right? So valences of, let's say, hydrogen would be +1. A valence of oxygen would be -2, integer. Valence of fluorine would be -1, etc. So the valence not only tells us about, so valence tells us about donation or receiving of electrons, and also the integer values, e.g. hydrogen would be +1, copper you'll have +1, +2. I think iron you have all sorts of, it's +1, it's +2, it's +3, that one, n. That one. So that's valence, right? Electrons at the outermost energy level of an atom are called valence electrons. So back to our atomic model here, the electrons that are at the outermost energy level would be on these ones, the 2s and the 3p. Right? Now those atoms, they're called valence electrons. They are the electrons that participate in the electron exchange during chemical reactions. Core electrons are all the electrons in the atom except the valence electrons. Right? So core electrons is all electrons in an atom except valence electrons, right? An element that has its valence energy level full is more stable and less likely to react than other elements with a valence level that is not full. So in other words, it's that which I keep saying. Right, when sodium reacts with chlorine to form sodium chloride or table salt, then the valence electrons in sodium is just 1, and it donates that electron to the chlorine, whose valence electron or valence value is -1. So now when that electron is added to the chlorine, then the valence on either becomes 0. And when that is 0, then it means the atoms have combined to form a molecule that is less reactive. So there's no need for them to share or exchange electrons. It doesn't mean they cannot be in ionic form, like when you dissolve salt in water, but it just means when it's pure crystal salt, then the likelihood of sodium wanting to react with a hydroxyl ion, for example, or chlorine wanting to react with hydrogen, for example, the probability of that happening is less because the valence electrons from the sodium and the valence electrons from chlorine have now exchanged with either atom and have resulted in some stability with either atom. So the whole point of nature is balance, and reactions are also about balance as well. So even at atomic level, balance still matters. So when something has a valence of +1, it must combine with something with a valence of -1, and then you can have a net charge or a net valence of 0 on the molecule. And then co-electrons would be the electrons closest to the atom that are not necessarily involved in the reaction of Mtulani. Alright, so let's quickly do this exercise 4.4 to test our knowledge on valence. So we've got potassium, we've got helium, we've got oxygen ion, and we've got magnesium ion. Not manganese, ne?
Okay.
Magnesium ion. Yes. So for potassium, what's the electron configuration? Let's quickly look it up on the periodic table. This is page 86. Okay, 103.
Oh.
Have you opened your periodic table?
No.
No need, ne? Yes, where is it?
You know what to do. What to do?
It's fine. It's fine. Yeah. So potassium. Let me just open a new slide. Potassium will have 1s2, 2s2. I get it's number 19. 2s2, 2p6. So that's 10. 3s2, that's 12. So that means we're short 7. And that means there should be 3p6. So that's 12, 14, 16, 18. And I think it should be 4d. Was it 4s1? Wait, where did they say the d orbitals appear? Is it in the 3rd or 4th energy level? Magdalene, do you remember? Where they say the d orbitals appear, is it in the 3rd level or 4th energy level? I don't remember. I'm just going to quickly check. Electron configuration. Okay, the 3rd energy level contains 1s orbital, 3p orbitals, and 5d orbitals. So before we even get to s1, then we must have 3d, right? So because we've got 2, 4, 10, 12, 18, then the d orbital should have 1. All right, we don't necessarily have to do the Aufbau diagram. You just have to state the G. All right, so that's the electron configuration. I think let's quickly view solutions. So this link is not working. Oh wow. Anyway, yeah, so the core electrons would be here. And remember, potassium is in group 1, so it has a valence integer of +1. So this would most likely be the valence electron. So in other words, in the electron configuration, potassium has this configuration, and its core electrons are from here, and this here would be valence electrons. So if you know how to do this configuration, then you'll be able to identify which ones are the core electrons and which ones are the valence electrons. And we can do the same for helium as well. Helium is number 2, so it's got 1s2. And that's pretty much it. That's the core, and it doesn't have valence electrons. Oxygen, ion. Oxygen is number 8, so it has a valence of -2. So if it's 8, then its configuration is 1s2, 2s2, 2p6. So that's 2, 4, 10. Yeah, for the iron, that's it. 2, 4. Otherwise, if it was just oxygen, it would be 2p4. Because the other 2 electrons would need to be added to give it a valence of 0. So when we add those, then this is it. So the core electrons, it's 8 core electrons and 2 valence electrons. And then magnesium ion, we can do the same calc. Magnesium is further down the periodic table, so its electron configuration would be a lot more confusing, I suppose. Yes, let's go. Touch, let's go. More than a regular textbook. Where's the periodic table, bruh? Did I skip it? I think I skipped it. No, it's at the beginning. Ugh. At least it's protected by Creative Commons, so that's nice. So magnesium is number 12, so we'll have 1s2, 2s2, that's 4, 2p6, that's 10, yeah, 2, 4, 10. And that's because the 3s2 electrons have fallen off and they've been donated. So the valence electrons are these 2. So it's got 2 valence electrons, and it's got 10 for the core electrons. And then, yeah, that's its configuration as an ion. So I didn't put the 3s2 because that's the configuration when it's not an ion. When it's not a cation, yeah. 105. Okay, right. Okay, so we're done with that. So the importance of understanding electron configuration. Yeah, so basically a reiteration of what I said. The valence of electrons of an atom will determine how they react with one another. So that's why we need to understand the electron configuration of atoms. But so far, I really have to ask, this class, just this part, has it been understandable?
No.
Not really. Where did I lose the...
Wow, that's a big question.
That's a big question. Fair enough.
Yeah.
I think this one needs more visual learning. The long and short of this chapter, right, and I don't mind going over it again, is that it gives us an understanding of what atoms would look like if we were to zoom in on them. If we were to shrink ourselves not too small to be inside them, but big enough to be able to observe one atom, then this is what we would see. So that's the whole point of this exercise, right? And then the second thing is we also need to understand the electron configuration. One, because electrons give us the electron charge that you find from a battery or anything that has electricity in it, because the chemical energy would then be converted to electrical energy. But not only that, as the atom itself, we want to see how it looks when it's stable, how it looks when we consider its valence, because that is what's going to set the basis for all types of chemical reactions that we're going to find, especially where the chemistry is literally just chemical. There's not much physicality in it. Like this physical chemistry where you can change the properties of substances by adjusting the pressure, temperature, and volume. So that's physical chemistry. So we're not doing that. What we're doing is looking at atoms, how they're shaped, and how they're configured on a periodic table. And we want to take that knowledge so that we can understand how chemical reactions are going to happen between different types of chemical elements. So in other words, when we know the difference between a hydrogen atom as an element, or rather a lithium as an element, right? A lithium atom as an element. And we also look at it as an element that can react, meaning it has valence electrons. Then when we know that elements like lithium, which are in the same group, tend to have a valence of +1, we know that they are more ready to react with elements that would receive an electron or two, such that if one group 1 metal or element is going to react with a group 8 element, for example, let's take in the case of hydrogen and oxygen, hydrogen being from group 1, because hydrogen has a valence of +1, you will need 2 hydrogens to combine with 1 oxygen, so that the -2 valence of oxygen can be neutralized by the +1 and the +1 of the 2 hydrogens that are going to combine with it. So that's the whole point of this exercise. And that's the high-level summary of it. We are basically understanding how electrons stay and move in an atom, or are configured or set in an atom, so that when we look at when an atom from a specific group in a periodic table reacts with another element from another group in a different thing in the same periodic table, what is the likelihood of the valence of each of these elements making it possible that they can react? So the nice thing is that nature has already provided us with concrete references that we can refer. Water, salt, stomach acid, sulfuric acid, ammonia, etc. Some of them we manufacture ourselves as humans, some we find in nature. Nevertheless, the ones that are naturally found, I think, have given a good basis to understand at least why we would say sodium has a valence of 1 and chlorine has a valence of -1. So because we have understood, or rather we're working on understanding how electrons in either sodium or chlorine are configured in each atom, then we will be able to see that sodium, because it has a valence of +1, because it in its electron configuration, it has an orbital that might be filled with 1 electron. Then because it is a valence of +1, it's willing to donate an electron. And after donating that electron, then the element that would be ready to receive that electron will react with it. But we can only understand that best when we understand electron configuration, valence, co-electrons, etc.
Hey guys, let me leave you guys here.
You wanna bounce?
I'm bouncing.
Alright, enjoy the match.
I hope so.
All right. How many people are you having over?
8.
8. That's party.
Nah, I'm hoping not for a party.
Hey, did you hear about pimps and hoes when we were at varsity?
Sis, what? Okay, wait. What is it, a club or what?
No. My friend and I organized our 21st. And then we used Balari money to theme it in pimps and hoes. Yo, bruh. Marupela was a groovist back then, so that's why it was inevitable. Anyway, enjoy. Don't burn the suburbs down. Alright. Yo, she's gone, eh? Okay, I can stop sharing the screen. So now yeah? I'll just dismiss this one. Alright, so valence is that it helps us understand how the electrons in an atom are configured. Like, you see how your keyboard is configured. There's QWERTY. You know, any keyboard, whether it's Mac or Windows, that's a configuration.
Okay.
Yeah. So now when we know this about different atoms and how to develop it for different atoms, then we can understand, okay, group 1, they'll always have a plus 1, comma 2, comma 2. Group 2, a plus 2, comma 2, comma 2. So when we do it as an ion, we drop the plus 2. When we do it as an atom, we keep that plus 2. That's the long and short of it. Right? And secondly, building a model of an atom. Right. I wanted to see something about electronegativity. Now, periodic table. Comes back to periodic table, right? So, there's different types of periodic tables. I'm going to show you another cool one. I wanted to show it with Nuguhle Mara. She had to go. I wanted to show you this periodic table, right? And the nice thing about this periodic table, Gori. So I don't have, wow. Okay, I'll just use paint. Yeah. Oh, let me use the PDF file. Open with Microsoft Edge. Alright, so I wanted to show you this now. So this periodic table illustrates all the elements, right? And then it shows you how we go from hydrogen to helium, I think. Lithium. Where's helium? Hey. Where's calcium? Oof. Okay, this is a bit confusing. But what they wanted to illustrate with this is how the number of electrons, as it increases, how you can visualize it in your mind, in your mind's eye. So like, you start with 1, and then as you increase, it loops like that. It goes back to the same group. And then it loops like that and going back to the same group again. That one. So your first 20 would end here. That's calcium, right? Potassium, argon, sulfur, phosphorus, aluminium, magnesium, neon, oxygen, nitrogen, lithium, boron, beryllium. Somewhere there should be helium. But the point is, someone was just being artistic about the science and was saying, you know what, I'm struggling to visualize this thing, but can't I visualize it based on just the electron configuration and maybe map it out somehow? Then they ended up having that spiral. Yeah. So, yeah. Then, so the arrangements of the elements in the periodic table, go in order from increasing of atomic number, right? So we can credit Dmitry Mendeleev. He didn't discover anything or any chemical element whatsoever. He didn't discover it. He didn't make, I'm not sure if he made breakthrough scientific discoveries. Maybe he did. But what I know is that he is credited for coming up with how the periodic table is configured. So before he developed this, lots of scientists had come up. Oh, boron electron configuration is this. What in is that? What in is that? And it's like, oh, okay, so we know all this information. He collects all that data, consolidates it, and then after it comes up with this. And then he says every period goes from, it's the rows are your periods, and groups are your columns. All right. So that's the long and short of Dmitry Mendeleev and the periodic table. Then important concepts include things like atomic radius. So that's literally, the atomic radius is the measure of the size of an atom. Ionization energy. Ionization energy. It's the energy needed to remove one electron from an atom in the gas phase. The ionization energy is different for each element, and we can also define second, third, fourth, etc. ionization energies. And these are energies required to remove the second, third, fourth, etc. Right? So when an element is in gas phase, then it requires some amount of energy. So to remove an electron in gas phase. Third, electron affinity, right? So affinity, do you know what affinity means?
Affinity.
English class now, English class. Affinity. So weird to type with a pen. Natural attraction, liking, or feeling of kinship, right? So, guess how physics. If you don't know that by now, I don't know when you're gonna figure it out. But guess how physics. So affinity in terms of chemistry, electron affinity rather. Electron affinity is how much an element wants electron. Right? And then we've got electronegativity. Electronegativity, which is the tendency of an atom to attract electrons. So these two are different. Do you want to know why? Or do you know why? Why electron affinity and electronegativity are different? All right. So this electronegativity ranges from 0.7 to 4, right? And this here we have francium, and here we've got fluorine. It's weird how it's the ones with F. But anyway. So electronegativity is the tendency. So tendency, ne? It's like a trend. It's like a inclination. How do I say inclination? Okay, a predisposition to think, act, or proceed in a particular way. Characteristic pattern or point of view. So this one falls off. A characteristic likelihood. Okay, So let's think about it like this. Yeah? So electronegativity is a number that you give to an atom. And you give it based on the predisposition of that atom to proceed to attract electrons. Yeah. Not necessarily that it wants to, just that property or it that it receive. Now, that can be measured, and it's measured on a scale of 0.7 to 4. So that if an element has a low electronegativity, that means something else than when an atom has a high electronegativity, which would mean something else as well. Yeah. That one. And then, so group kichelache vertically and period kichelache horizontal. Right, so you go across. Yeah. And then for each element, we can give this period, for each element, we can give a period number and group number. So for example, B, which I think is boron, is in period 2 and group 13. See? Group 13. Yeah. Period 2, group 13. So it's like coordinates.
Yeah, coordinates, yeah.
It's like coordinates, right? You go across, you go up. So you go across 13, you go down 2. More or less. Right? And then there's a S block. So remember electron configuration, eh? This stuff. It goes back to the periodic table. Right, so those s orbitals, né? Those p orbitals, and then the d orbital. So we note that the period number gives the energy level that is being filled. So for example, phosphorus is in the 3rd period in group 15. Looking at this, then it's the p orbital that is being filled. So back on our ne? Oh yeah, by the way, remember, yes, because potassium is somewhere here, ne? It donates electrons. It has a likelihood of donating electrons because it wants to keep its electrons stable within an S range, right? Because valence is D. Its valence is in the D block. Alright. So the electron configuration of phosphorus is the electron configuration of neon. And then, yeah. So since phosphorus is in the 3rd group, in the P block, 1, 2, 3. Phosphorus is here, right? So its electron configuration, so it must have 3 electrons in the P shell. Yeah, something like that. And then lastly, those concepts that we spoke of, ionization energy, electronegativity. So this one, electronegativity increases with groups. The ionization energy increases with the group. And atomic radius which is the size of an atom, really. I'll just erase this here. So this one decreases with the groups. What does this mean? It means the atomic radius of elements here is always larger than the atomic radius of elements in group 1. The atom gram, they tend to be larger in size than the atom gram.
Okay.
That's why even when we draw hydrogen with oxygen in a molecule of water, when you draw them, the hydrogens always look smaller.
Okay.
Alright? Because the radius of oxygen is much larger than the radius of hydrogen. Yeah. Okay. So then here, this table refer all the elements in period 3. So the elements in period 3 and the types of compounds that they form, right? So sodium, in a chloride, it also has an oxide like water because group 1, it's about 2 sodiums to 1 oxygen. And it's got valence electrons at 3s1, right? Its atomic radius decreases across period. Okay, maybe we'll look at this discussion a bit later. Magnesium has a chloride. Chlorine tends to receive 1 electron, but since magnesium, MO group 2, tends to donate 2 electrons. So if magnesium react a chlorine failure, then 1 magnesium must pair with 2 chlorines, because chlorines takes 1, but magnesium gives 2, so 2 chlorines will take 1 of each. Aluminium chloride tends to give 3 electrons, so it will pair with 3 chlorines. Silicon tends to give 4 electrons, so it will pair with 4 chlorines to make a silicon chloride. Phosphorus tends to give 5 electrons, but in some cases it will give 3, depending on what's the process and how is it reacting. Sulfur, yes, sulfur gives 2. Hold up. That's sulfur, right? Sulfur, in dioxide, the trioxide, lady SO4. I thought again, sulfur is a monster. I don't like sulfur. I honestly don't like sulfur. Then it can be the one receiving electrons, like if it is a hydrogen sulfide. You know hydrogen sulfide?
Mm-hmm.
The smell of rotten eggs. H2S, you don't know it? Yeah, so you can make that in a lab and you can also have it at my RCNE. Yeah, so in that case it receives electron. Like sulfur-ish, it's anyway, that's the long and short of it. Yeah, so that's pretty much it. So I wanted to discuss things like electronegativity, because if we don't understand them, then doing things like chemical bonding becomes challenging. Because once we get to this, that valence electrons, hydrogen is a valence electron, chlorine is receive a 1, then you have a pair. Sorry, so that's more or less how it works. Then there's the different types of bonds, and then when you have to discuss things like intermolecular and interatomic forces, if you don't understand electronegativity and how it changes across the periodic table, it kind of gets difficult to answer these ones.